All right, folks, welcome back. We're going to jump into section 1.3, evaluating limits analytically, and we'll be splitting these notes into two parts. Here's part one. If you recall from our previous discussion, our intro to limits, I talked about three different ways to evaluate a limit, and those were the following. Numerically, we can look at a table of values and see what the limit of a function is from a table of values. We could look at the graph of a function and see if the graph can tell us what the limit is. And then the third technique, the one we'll be talking about today, is analytical. And the third technique, the analytical technique, is the one that will give us an exact limit. The other two are just estimates. And 9 times out of 10, that estimate's going to be fine, but of course we'll look at special cases where we definitely need the analytical techniques. And then the other thing about the analytical techniques, it involves something that many of you are struggle with, and that is algebra. No, just kidding. Yeah, so we're going to use a lot of algebra within this section to analytically determine the limit of a function. Okay, as just a little reminder about limits from our previous lesson, a limit, our informal definition of a limit, is the height of the graph that we approach, that the function approaches for a given x value. And let's take a look here. 3 primary analytical techniques we're going to talk about: direct substitution, dividing out, and rationalizing. And they we would always choose to try them in this order. Because the easiest way to evaluate a limit analytically is direct substitution. If that doesn't work, and we'll see some reasons why it might not work, then we would try dividing out a common factor. Finally, we might need to rationalize a function in order to find a limit. And if any of these three, this is it for evaluating limits analytically. We're only going to look at those 3 different techniques. If any of those don't work, well, then we must rely on theorems for help. So there will be a couple theorems that go along with this section that we'll learn about and then apply. All right, so let's look at the first example. Determine the following limit, then identify what strategy you used. Well, the limit of x squared as x approaches 3. I know that the function x squared is continuous for all real numbers, so there's no discontinuities or anything there that's going to act crazy. So I plug in 3 there and I get 3 squared. So the answer to that is 9. And what technique did I use? That's just direct substitution. And direct substitution is just like it sounds. You're substituting in a value for the function. So we had 3 squared, and that's 9. So that's the technique that we use there. All right, so the second example we're looking at here, it asks the question, are the following functions equivalent? We have f of x equals x minus 3, and g of x equals the quantity x squared minus x minus 6, all divided by x plus 2. So are these two functions equivalent? Well, certainly not. They don't even look close to equivalent. But let's see what happens if we do a little bit of algebra on the function g. So I'm going to start by seeing if I can factor that numerator. I think that's pretty easy. Quadratic to factor. Factors into the quantity x minus 3 and the quantity x plus 2. And then I have x plus 2 in my denominator. And right now I know you're tempted to just cross those out, but we're not going to do that because then we would lose visibility to some of the function if I cross out those 2 x plus 2's. So here's what I would say. We know f of x equals x plus 3, and if I were to think about crossing out these x plus 2's, I would be left with x minus 3. So those functions look equivalent when I cross out the x plus 2's. I'm going to leave the x plus 2's there, though. So here's what I want to say. F of x equals g of x for values of x not equal to -2. And the reason why is because if we plug in -2 to the function f, we get -2 minus 3, that's just -5. But if I plug in -2 to g of x, I'm going to get 0 divided by 0, and that's undefined. So g of x is actually not defined for value of x equals -2. So what I can say is g of x equals x minus 3 for x not equal to negative 2. So those functions are equivalent everywhere on the real number line except at x equals negative 2, because negative 2 is not in the domain of G. And why are we talking about this? Because this can help us with limits. And you'll see how that can help us with limits in a few short minutes. Okay, well, let's move down to some more examples here. Determine the following limits, then identify what strategies you used. So example 3, we're going to start with direct substitution. Okay, we've run into our first problem. I tried direct substitution here. I want to find the limit of x minus 2 divided by x cubed minus 8 as x approaches 2. So I plug in 2 and I get 0 divided by 0. Well, we cannot tell the limit from this form. So one of the big takeaways from today's lesson needs to be, if you're ever using direct substitution when evaluating limits and you get 0 divided by 0, you're not done. You have more work to do. You somehow need to find a way to evaluate the limit without getting 0 divided by 0. And I'm going to show you how we're going to do that. So the next strategy we would try is divide out. And I know this. If I plug in 2 to my denominator and I get 0, that means x minus 2 has to be a factor of my denominator. So x minus 2 is going to factor into, x cubed minus 8 is going to factor into x minus 2 times something else. Well, x cubed minus 8 is a difference between two cubes. And there is a format for there's like a shortcut for remembering how to factor a difference between two cubes, and I never remember what that shortcut is. So I'm going to actually step back into pre-calculus land here and show you the long way to do that. So if I know that, probably shouldn't go highlight there. So if I know that x cubed minus 8 has a factor of x minus 2, that means I should be able to divide x cubed minus 8 by x minus 2 and get no remainder. Well, how many of you remember this? What I'm doing here is synthetic division. Take the 1 down, 2 times 1 is 2, 0 plus 2 is 2. 2 times 2 is 4. The 4 up here, 0 plus 4 is 2 times 4 is 8. Negative 8 plus 8 is 0. So I now have the 3 coefficients for my quotient. This work tells me that x cubed minus 8 has to equal x minus 2, and then x squared plus 2x plus 4. And I know this might be digging a little bit deep back into the pre-calculus skills here, but if I divide x cubed minus 8 by x minus 2, and here's the 0 of 2 that I divided by, the coefficients I get here are the coefficients of the polynomial, 1 degree less than what we started with. And then I have a remainder of 0, so I know the product of these two factors gives me x cubed minus 8. So one of the things I guess I should probably talk about now is I am not going to spend a week or two at the beginning of the year reviewing pre-calculus. What I will do is go through anytime somebody has a question about a pre-calculus topic, certainly I'll go ahead and spend some class time talking about that. That's why I did this here today. And if you want to do a little bit more research, this is synthetic division. Achieves the same result as polynomial long division if you want to take a look and do some review on either of those two topics. Okay, so I have my other factor here. The whole point of this was I needed x squared plus 2x plus 4. So I'm going to jump back here. X squared plus 2x plus 4. Okay, so what does dividing out mean? It means that I'm going to divide out a common factor. Now, the function that I have left here is not equivalent to the original function, because at x equals 2, the original function is undefined. But remember this from our lesson, our previous lesson that where we talked about limits. We don't care about the value of the function at the x value of interest. So I don't care about the value of the function when x equals 2. In fact, that value can often be misleading. What I care about is how the function behaves right before x equals 2 and right after x equals 2. So now I can, because I don't care about what the function does at x equals 2, I can ignore these factors that divide out, and I can just look at what happens when I evaluate the limit of what's left. So let's go back here and just kind of look at our original problem. Our original problem was find the limit of x minus 2 over x cubed minus 8 as x approaches 2. And that gave us 0 divided by 0. It doesn't work. Well, I'm claiming that we don't care about the function at x equals 2. We just care about how the function behaves near x equals 2. So I have an equivalent function here. After I divide out a common factor, and I can evaluate the limit of that function as x approaches 2. And for this, I can use direct substitution. Pandemonium, pandemonium. Guys, it's the mailman. Calm down. Okay, so direct substitution here gives me, let's see, we're going to have 1 divided by 2 squared plus 2 times 2 plus 4. 2 squared is 4. 2 times 2 is 4. 4. So that gives me 1/12. And that is the answer to this problem. The limit of x minus 2 over x cubed minus 8 as x approaches 2 is 1/12. Let's move on to example 4. I'm going to find the limit of this function, square root of x plus 1, all minus 2, divided by the quantity x minus 3. I'm going to look at that limit as x approaches 3. As is always the case, the first thing we're going to try is direct substitution. So that's going to give me square root of 3 plus 1, all minus 2, divided by 3 minus 3. Well, let's see. 3 plus 1 is 4. Square root of 4 is 2. 2 minus 2 is 0. And I have 3 minus 3, and that is 0. Uh-oh. As you recall from the previous example, anytime I have this, 0 divided by 0, I cannot determine the limit from this form. So I need another strategy. Well, in this case, we're not going to try dividing out because there's no way to factor either the numerator or the denominator here. We're going to try that other procedure I mentioned. That's going to be to rationalize. What I'm going to do is multiply the numerator of this function by its conjugate. Holy cow, that's a big word from the past. Let's see if we can remember what a conjugate is. So my original function is x plus 1 minus 2, all divided by x minus 3. The conjugate of my numerator is x plus 1, that's square root, plus 2. Now, I can't multiply this function by something without changing its value. The only way I can multiply it by something and not change its value is if that something is equivalent to 1. So I need to multiply by the conjugate divided by itself. So I need to have x plus 1 all plus 2 here. I need to multiply by the conjugate divided by the conjugate, and then I'm not changing the value of the function because I'm multiplying by something that's equivalent to 1. So let's see what happens when we do this. When I multiply, I'm first going to work on the numerators. When I multiply the square root of x plus 1 times the square root of x plus 1, I get x plus 1. And then when I multiply that, I multiplied the two first terms. You can think of this like foiling, first, outer, inner, last. So I multiplied the two first terms. Now I'm going to multiply the two outer terms, square root of x plus 1 times positive 2. So that's going to give me 2 times the square root of x plus 1. Now I have to do the inner terms, this negative 2 times the square root of x plus 1. So that gives me negative 2 times the square root of x plus 1. And last but not least, I got to do the last terms, negative 2 times positive 2, so that's minus 4. And don't forget, we have a denominator. My denominator is x minus 3, and I'm going to multiply that by this denominator, which is the square root of x plus 1 plus 2. I'm not going to expand that, because if I were to expand that, it would just get messy. Trust me, I've tried it before. I know it gets messier. And what I actually need is I need my denominator to look like this, so I'm going to keep it in this factored form because there's some magic that happens next. So let's take a look at our numerator and simplify. Hopefully you've noticed that you have a 2 times the square root of x plus 1 minus that same quantity. So those two bad boys cancel out. And now I just have x plus 1 minus 4, and that simplifies to x minus 3. In my denominator, I have a factor of x minus 3. That's a beautiful thing. So let's just talk about what we just did here. I rationalized my numerator. By rationalizing it, it no longer has an irrational square root function in it. I've rationalized my numerator, but I also was able to get a factor that cancels. That factor of x minus 3 cancels, and I'm just left with this factor in my denominator. I don't care that it's could be an irrational factor because the problem I was having was the 3. The x minus 3 caused a 0 in my denominator, and I think I got rid of that now. So let's take a look at the original problem versus what we have now. The original problem is this. It's the same as this. On this, we're going to try direct substitution and see what happens. 3 plus 1 is 4. Square root of 4 is 2. 2 plus 2 is 4. I have my answer. This limit is 1/4. Okay, so 2 different examples where we tried different strategies, but we always go back to direct substitution. Once we've simplified a function and gotten rid of whatever 0 was causing us issues in the denominator, then we go back and try direct substitution. The next example is a little more complicated. It's going to involve some more algebra than what we just did, and so I'm going to start by, the way I start all these problems, and that's try direct substitution. Okay, direct substitution, I have to substitute in -3 there. I'm not a human calculator, so I'm going to jump over my calculator and see if I get a little assist from the calculator on this one. So I have to do 2 times -3 cubed minus 7 times -3 squared minus 33 times -3 plus 18. Grip it and rip it, and I get 0. Holy cow. Direct substitution there gives me a 0. How about my denominator? Well, 3 squared minus 9, that's 0 also. So direct substitution gives me 0 divided by 0. Remember, we cannot use that form to evaluate the limit. So we've got to do some other work. Let's analyze this denominator here real quick. All right, so analyzing this denominator, because I've done a little bit of algebra in my time, I know this is a difference between 2 perfect squares, and it factors. So x squared minus 9 factors into x minus 3 and x plus 3. Okay, so this actually is kind of helpful. I was looking for the limit as x approaches -3. I know if I plug -3 in here, I get a 0. And that's why I got a 0 in my denominator. Well, if I get a 0 in my numerator, then x plus 3 also has to be a factor of that numerator. So let's divide out the numerator by x plus 3 and see what happens. In fact, I'm going to set up the synthetic division for that to see what our remaining factor is. So when we divide this cubic by a linear term, x plus 3, I'm going to end up with a quadratic term. When I divide a cubic by a linear term, I end up with a quadratic. So let's see how that works. Okay, so this 0 right here means that we have a remainder of 0 when we divide out the numerator by the factor x plus 3. So what does that mean for us? That means that 2x cubed minus 7x squared minus 33x plus 18 is equal to x plus 3 times quantity 2x squared minus 13x plus 6. Okay, so that's great. So step 1 was direct substitution. Step 2 was recognizing that we had a perfect square, the difference between two perfect squares in our denominator, and that can be factored. Step 3 was recognizing that we could use synthetic division to find out what the other factor is of the numerator. Step 4 was writing out those two factors. And step 5 is going to be going back to our original statement. Okay, again, I'm rewriting the limit as this simplified function because I have a factor of x plus 3 that's going to cancel from both the numerator and the denominator. I'm not showing that canceling here. Hopefully you can follow along from all the work I've done so far. At this point, we're going to try our friend direct substitution. Okay, folks, there you have it. Through a little bit of simplification there, we've got 63 over negative 6, which simplifies to negative 21 over 2. And just a note here, you're gonna notice that I have a personal preference in AP Calculus of using, some of you might call this an improper fraction, and I'm not using a decimal. We're going to make this point throughout the year, but decimal problems are where typically when we're doing application problems and there's some approximations involved. Otherwise, we're going to use exact answers all the time. And I know that if you divide it out, negative 21 by 2, let's see, what would that give you? Negative 10.5. And I know that is an exact answer, but oftentimes we think of the decimals that we might be rounding as approximate values, whereas the fractions are exact. Okay, this video is getting a little long, so I want to shut it down here. But I do want to say one last thing, and it actually trickles over onto the next page. I've made a point of saying things like this in this video, that I've made a point of saying we cannot tell the limit from this form, 0 divided by 0, and that showed up several different times. Well, that 0 divided by 0 has a name, and we're going to call that indeterminate form. And why do we call it indeterminate form? Because we cannot determine the limit from this form. It's indeterminate. So anytime you get 0 divided by 0, we got to do a little work to determine what the limit is. Okay, we're going to shut it down now and finish off these notes in a second part of the video.